All right, everybody. Part 2, 10.1, graphing square root functions. Way earlier in the year, I said, okay, everybody, we're going to learn about transformations and it's going to follow you around the rest of the year. Well, I wasn't joking. As you can see, we have all these transformations listed here, how those transformations actually look algebraically within the function. And then, of course, we have examples. I'm just going to go over them quickly. Horizontal translation, meaning that your graph is going to shift left or right. As you know, you're adding or subtracting numbers inside the function. Remember, inside means inside the name. If it's a square root function, that means inside the square root. So remember also it's opposite land, at least that's what I called it. So if you see x minus 2 compared to the parent graph that wouldn't have the minus 2, this is going to translate 2 units to the right. Plus 3 inside the function, 3 units to the left. Vertical translations, remember that's going to shift the graph, I keep saying graph, up or down, and that's the function is here, and then you're adding a number outside of it. So the function, a square root function, here's the square root of x. This plus 7's outside, so that's going to translate 7 units up. This minus 1's outside of the function, so it's translate 1 unit down. Reflection, and it's going to be a reflection in the x or the y-axis. They're using the word flip, which I don't know about that. But inside the function, it means the opposite x on the opposite side of the y-axis is going to give that output. So this is going to be a reflection in the y-axis. This negative on the outside of the function is going to say whatever y was before, it's the opposite value. So that's going to be reflection in the x-axis, right? It's going to take the parent function square root of x and then make that y value negative, which puts it on the other side of the x-axis. Horizontal stretches or shrinks, those are dilations. Remember, if it's horizontal, then you're shrinking away or towards, away from, or toward the y-axis. And I can't show you with my hands right now, but you probably remember this. You're pushing inward towards the y-axis or pulling away from it. If it's a shrink, you're pushing towards it. If it's a stretch, you're pulling away from it. Remember, it's opposite land. So if it's 3 inside, it's a multiplier, right? It's a factor multiplying x inside the function. It's a shrink by a factor of 1/3, right? Because it's essentially saying all those y values are going to be towards the y-axis. Same thing with 1/2. It's going to be opposite land, so that's actually going to be a horizontal stretch by a factor of 2. And remember, it's the reciprocal inside of the function, which is the actual factor of. Okay, vertical stretches and shrinks. Another dilation. This is away or toward the x-axis, and this one makes a little more sense. Remember, a is outside the function for a vertical stretch or shrink. And so if it's 4, it's a stretch by a factor of 4. It's taking all of the y values that were there in the parent function and it's multiplying by 4. So they're going to be 4 times further away from the x-axis. And if it's a fraction outside the function, it's going to multiply all the original y values of the parent function by 1/5. That means it's going to shrink towards the x-axis. Okay, graph g of x is equal to negative square root of x minus 2. Let's start from x. What's the closest operation to x? It's minus 2. So compared to the parent function, comparing to the graph of the parent function, f of x is equal to square root of x, we have a minus 2. That's inside the function. That's a horizontal translation, 2 units to the right. So whereas the parent function originated at 0, 0, this one's going to originate at 2, 0. And that's important because remember, this radicand, if you solve that radicand in the inequality of the radicand being greater than or equal to 0, so x minus 2 has to be greater than or equal to 0 in order to be able to evaluate a real number, right? Because you can't take square root of negatives. If you add 2 to both sides using the addition property of inequality, you get x is greater than or equal to 2. So this is where the graph originates. And of course, we see that here. Okay, now notice what they did here. Well, I forgot. Sorry, that's the translation, 2 units to the right. Then we have a negative outside the function. That's going to take all of the original y values, and it's going to make them the opposite sign. If all the y values are the opposite sign, then they're going to be reflected in the x-axis. Okay, Notice what they did. Instead of selecting numbers that would result in a perfect square in the radicand, now notice that you're subtracting 2. So you'd want to select like 2, because 2 minus 2 is 0. 0 is a perfect square. You can take the square root of that, right? 1 is also a perfect square. So you'd want to choose x equals 3. So 3 minus 2 equals 1, right? And if you want to get another perfect square, like 4 is a perfect square, what would x have to be in order to get 4 inside the radicand? X would have to be 6. So in fact, we can do that here, because 6 minus 2 is 4. The square root of 4 is 2, negative. So that's negative 2. Now, you don't have to find perfect squares under the radicand, right? You don't have to. You can just use, they just went in sequential order, 2, 3, 4, 5. You can take 5 minus 2 and get 3 and take the square root of 3. Remember, though, if you're taking the square root of a non-perfect square, you get an irrational number. That's a decimal that goes on forever and never ends. So I think we substituted 5 in here. 5 minus 2 is 3. The square root of 3, I think I actually have to do it this way. Can I do that? No, I can't. So it's 3. Square root of 3 is 1.73205. And this is actually a decimal that would go on forever and never end. So we're going to have to just kind of estimate that. Maybe to the nearest tenth, I think is what they're doing here. So that's 1 7/10. And then it's going to be negative because of that reflection. So that's negative 1 7/10. So not very hard, pretty easy, pretty straightforward. If you know how to graph functions in your previous, based on the previous functions we've learned in this class, should be pretty straightforward. Okay, let's do this last problem. Let g of x is equal to negative 2 times the square root of x minus 3 minus 2. First, describe the transformations from the graph of f of x equals the square root of x, that's the parent graph, to the graph of g. And then we're going to have to graph g. Okay, let's do part A. I think we discussed the order that you list your transformations in. It's in order of operations order. So if you are x, what's the first thing that's going to happen to you that's different than the parent function? Minus 3. That minus 3 is going to be a vertical or horizontal translation. I can hear you. Horizontal translation. And that's going to be what direction? Well, it's the opposite of the sign that's there, 3 units to the right. Or I'm just going to say right 3 to save you having to watch me write more things. Okay? Next transformation, well, the next thing that would happen is this would be multiplied by negative 2, right? So we'll start with the negative. If you multiply by a negative, that's going to, on the outside of the function, that's a reflection in the, and hopefully you're thinking about this, whatever the y values were before inside the function, which is like the parent function, whatever the y values are before, now they're negated. So those y values are on the opposite side of the x-axis, so that's a reflection in the x-axis. Okay, then multiplying by 2. This 2 is outside the function, right? And the absolute value of this multiplier is positive 2. That's greater than 1. That means that you're going to make all those values further from the x-axis than they would have been before. So this is a vertical stretch, and that's supposed to be a dot, okay. Vertical stretch by a factor of 2, not negative 2. The negative was used in the reflection. Oops. Whoa. And then the last one is going to be this minus 2, which is outside the function, outside the square root. And so that's going to be a vertical translation. Down 2. Okay, as far as graphing this thing goes, I'm just going to make a table. Let's just focus on making a table, and that will serve all of our purposes here. So if I have my input, which would be x, and my output, g of x. Okay. So first thing I want to do is I want to determine where my graph originates. It should, in the parent function, originate at 0, 0. But on this one, it has these translations and all of this kind of stuff, right? So that's going to change things. So what I'm going to do is I'm going to take the radicand and write it. I'm going to take the radicand, and you can see the summary here. It's in the way. I'm just going to work underneath this. I'm going to take the radicand, and I'm going to write it as an inequality that has to be greater than or equal to 0. Why? Because you can only take square roots of 0 or positive numbers, not negative numbers. If I solve that using the addition property of inequality, I get x is greater than or equal to 3. That means my graph originates at 3. So if I substitute 3 in for x, 3 minus 3 is 0. Square root of 0 is 0. Times negative 2 is 0. Minus 2 is negative 2. Okay, now, this reflected in the x-axis. Did it reflect in the y-axis? No, in the x-axis. So I don't know if you can still see this one up here. If it reflects in the x-axis, the graph is still going to stretch to the right. So the next number I'm going to choose is going to be greater than 3. But I'm going to be smart here. I want to choose x values, where if you evaluate what's inside the radicand, you get a perfect square. Well, let's see. What's the first perfect square after 0? X minus 3. I want that to be a perfect square. I want it to be the next perfect square above 0 is 1. I also want x minus 3 to be the next perfect square above 1. That's equal to 4. And then I want x minus 3 is equal to the next perfect square, which is 9. So then I'm going to solve for x. So I want x to be 4. I want x to be 7. And I want x to be 12. If you don't know why I'm doing this, watch this. 4, 7, 12. If I substitute 4 into this function, 4 minus 3 is 1. What's the square root of 1? 1. 1 times negative 2? Negative 2 minus 2, negative 4. Why do I want 7? Because 7 minus 3 is 4. What's the square root of 4? 2. We're only taking the principal square root, not the negative, by the way. Square root of 4 is 2. 2 times negative 2 is negative 4. Negative 4 minus 2 is negative 6. And I see a pattern emerging here. 12. 12 minus 3 is 9. The square root of 9 is 3. 3 times negative 2 is negative 6. Minus 2 is negative 8. And that's really enough numbers. I think if you have 4 numbers, at least 4 inputs and outputs, you can graph a square root function. That was really fast, everybody. I was trying to get within this, the time limits for YouTube, but if you have any questions, as always, let me know on Google Classroom. And remember, you can watch these videos over and over again. You're an amazing class. I hope you're doing very well out there. Talk to you later. Bye.